So today is the starting part of the exciting thing in epidemiology. It's very, very important to come and make sure that you're awake for next Monday. It might be the most important thing about epidemiology, okay, in the consideration of confounding. Okay, confounding, yeah. But today we are talking about something also important, but not that difficult to understand. It's pretty straightforward and very simple math. So don't worry too much, but it's also very important. Risk and relative risk. I think I have made it pretty clear about how we use the idea of risk for the purpose of comparison in epidemiology. Right? We could either using prevalence or incidence, no matter it's cumulative incidence or incidence density, okay, to estimate the or describe the risk for a specific group of people. Yeah. So I will revisit and make it like a review about how to define risk in the very beginning. And then I have to go to the details about how we do the assessment for association in epidemiological studies. Because I'm going to introduce a tool that's called RR. It could be the abbreviation for many different kind of things. But R is so-called relative risk. It's a tool to help us to struggle through the epi journey from association to correlationship. So I will emphasize it again and give you the idea about how to consider it in a lecture on Monday. So today you just need to pay attention to what is so-called relative risk and how we define it with a study with different study design. Okay, so the idea of relative risk is very important. R equal to R, R equal to OR. R here is a relative risk, but in core study, it's a rate ratio. It's pretty straightforward. We just use the rate from the exposed group divided by the rate of the unexposed group. Then we could get the relative risk estimation for core studies. But for a case control study, it's not that straightforward because we don't have the denominator for the calculation of incidence or prevalence at all, right? So we have to apply or adopt the idea about odds, ODDS, to develop something called odds ratio for the estimation of relative risk in case control study or cross-sectional studies. Okay, that's the key point for the lecture. And why is that? Why is it important? I can tell you now. This is the way we simplify the scenario for a lot of numbers. We could use one single indicator, which is RR, no matter it's a core study or it's a case control study, just one single number. Okay, so it's very straightforward. It's very helpful for us to consider the information from no matter the news or studies or anything. I just need to use a 2x2 table and I could generate a single indicator about the relative risk, no matter what kind of study design it was. Okay, so that's why it's important. Okay, risk is not far away, or it's not a very ancient idea to use the concept of risk for comparison. There's a very old book written by Chang. He was born in 1620 and died in 1674. So basically, he's an old man, right, living in the 17th century. But he was the first one to use the idea of risk for the purpose of comparison. And the book he wrote is the Observations on the Bills of Mortality. Bills means that there is a note put on the board to show how many people died for people living in different places in London or England. Okay? But in the past, people only pay attention to the number of deaths. Does it matter? No one really cares. But he was the first one to do the calculation, which is very simple, division. They use the number of people died in jails or prisons, divided by the number stay in the prison for a year, for example, in the beginning. That's the idea about what? Cumulative incidence of mortality, of death, right? And then he did exactly the same thing for the people in London and find out that the rate or the risk of people dying or the prisoners are much, much higher compared to the risk or mortality rate for people living in London. Okay, so that's the origin about the idea about relative risk. It's not a long time ago, only 200 or 300 years ago. But we have been using mathematics to sort out a lot of daily living things or problems for thousands of years. Right? But it's pretty late that we start to use the idea of relative risk for the comparison, for the purpose of comparison. And we could make a better conclusion, right, because of this. Okay, so, but in general, risk is the probability of something, but it's not limited to probability now, because probability sounds like a proportion, which is from 0 to 1, right? But now extend the idea to rates. So it could be something with a unit, like incidence density, right? Number of events divided by person years or person time. Something happened in a defined setting during a specific period or specific time point. This is the general idea of risk. Now, talking about risk, then what's the life event could be considered in the numerator? It could be death, right? Death is the end of life, and no one can escape from it, right? So it's pretty important, and it's the first thing we have to study when we are talking about a disease, an emerging disease, or the threat or the burden of the disease. Death is generally the first one we talk about. Or it could be the occurrence of that disease, or the recurrence of the disease, or the recovery from disease, or disability caused by the disease, right? But we might need to use the other indicator about the disability, like a disability adjusted life year loss, or something, YPLL, something like that. Or loss of workforce. So this is the other kind of the indicator about life events, but it might not be so related to risks anymore. I just tell you that it could be as broad as something like loss of workforce and the years of potential life lost. It could be years or loss of workforce. If we consider this kind of thing with these indicators, do you know what is the worst disease, or which disease got the highest loss of workforce in human being? Top one is influenza. Right? The second one, low back pain. Yeah? So the story will be totally different if we use the other alternative indicators about health events. Yeah, but in epidemiology, we care more about death and occurrence of diseases. That's why I put in red words. Okay, review the idea about incidence. In the calculation of incidence, we highlight the idea about new cases. It's about status change. People without the disease and then transfer into the situation with the disease. It could be cumulative incidence. So we just follow up that group of people in a period of time, and we use the people at the beginning point as the denominator, and the people who got the disease during the follow-up period as the numerator. And that's the cumulative incidence. It's pretty easier to do at the national level. But for incidence density, that's not so straightforward because we need to have the precise time information about what happened and who is still alive or who died on a specific date or time to calculate the incidence density. So if possible, we prefer to use incidence density. But sometimes we have no choice to use cumulative incidence as a substitution of it. Okay, but using incidence might be something important when we are performing etiology study at the population level, because we want to know what makes people get higher risk of incidence of disease or lower risk of. Okay, and prevalence is the idea of emphasizing existing cases. So it's just a measure of the status at a specific time point or a period of time. So you need to specify a time duration if you are calculating the period prevalence. But it's more useful for the purpose of health administration for research about it, because you need to know the total number, the prevalence of people with a specific disease in order to do the management of the staff or the medical resources. So that's the review for what we have. Okay, and here's the other review about mathematics. Okay, probability and proportion are very similar things, which is basically a number from 0 to 1. 0 means that it's not possible to happen. 1 means that 100% to happen. Right? It's very straightforward. But what about ratio? Is it different or the same? Yeah, it's a little bit different. When we are calculating probability or proportion, the numerator has to be part of the denominator. Like if we want to calculate the probability or proportion of men in the classroom, men has to be part of all the people in the classroom, right? So that's how we calculate the probability or proportion. Right? But for ratio, it's the same. The calculation is the same. A number divided by the other number, right? But they don't belong to each other, like sex ratio, right? Number of men divided by number of women. They don't belong to each other. Although the calculation is the same, it's about division, but the meaning in the background will be different. Okay, so you need to just recall this kind of very basic maths. So when we're trying to perform the assessment of association in epidemiologic studies, we have to use the idea about ratio of risks. Risk is a number. It could be prevalence or incidence. But we could do the calculation of the ratio, which is the outcome risk in exposed divided by outcome risk of non-exposed. So this is the idea of cohort study, which is basically comparing the people with exposure to the ones without the exposure. That's the basic idea. So the key question is asking how strong the effect is for the exposure. Okay. In the calculation of ratio, this is so-called multiplicative model. So in other words, we use the ratio to develop this sophisticated statistical analysis method, like modeling, logist regression, the regression thing. But we could also do the calculation for the difference of risks, which is the outcome risk in exposed minus the outcome risk in non-exposed. And this is so-called additive model. And the key question is how much they differ. But in epidemiology, we prefer to use that one because most of the sophisticated statistical method in modeling were developed based on the multiplicative model. Yeah, that's why we emphasize the idea about our ratio of risks rather than the difference of risks. This is more useful for the research about health administration or health policy, blah, blah, blah. But in epidemiology, we prefer to use the ratio of risks or relative risks. And the other thing about the assessment of association in epidemiology is that we need to create a great basic scientific design for any epidemiological study. And basically what we do is to do the observation and find out this might be a public health issue. And then we try to do the measurement for exposure or the disease status in the population. And then we try to perform the comparison. But observation might be the first, the starting point to do it. But how to do the measurement and how to do the data comparison, that's the key issue in epidemiology. Okay, so the concept of the comparison group, no matter is for the control, which means the one without the disease in the population, or the non-exposed group in the cohort. That's all about using the concept of comparison group for epidemiological research. And our task or our job is to ensure they are comparable to each other. And the most essential thing is confounding control. I'll try to manage the confounding at different stages. Okay, so we have to make sure that the comparison works or they are comparable to each other. Because it's a kind of dilemma for biologic or human subject study. And nowadays we pay more attention about the well-being, even if for animals. But we pay even more attention to human subject study. So we cannot manipulate all the exposure. Sometimes it's not possible to manipulate all the exposure, like genetic background, right? Or age, we cannot manipulate. Unless we invent time machine, right? So we cannot manipulate something, the fact about time or age. So we have to develop a lot of epidemiological methods to ensure that even if these two comparison groups are different in different aspects, but we could still perform a better comparison. So it's critical to maintain basic scientific design for study. Okay, and like what I said before, there are different levels of the etiology study. It could be as small as molecular level, like insulin deficiency is the reason for type 1 diabetes. Before we know that, we have nothing to do with it. We cannot treat or even know anything about diabetes. But at population level, epidemiology is the tool or the weapon we have about the etiology, the causes of disease. Incidence and the prevalence are the two basic indicators about the risk of the disease, right? But in nature or in practice, the people are coming and going, right? Even if you try to maintain or trace every single in the population, it's very unlikely to keep every single one, especially when you have a long follow-up period. So for most of change, it's dynamic, right? And prevalence is more about static views of the health events. So if possible, we are going to use the incidence because it's more closer to the nature of the real situation on the Earth. So we have to use incidence and prevalence as a tool to do the linkage between individual exposure to the disease onset. Okay, it's important, individual level. For most of epidemiological study, we have to use the information at individual level, no matter for exposure or disease status. If we don't, then it's so-called ecological fallacy, like what we mentioned on Monday. So relative risk is simply defined as an estimation of the association between exposure and outcome. So it's basically a calculation of division. And in Cohort study, it's called rate ratio, the rate of the exposed group divided by the rate of the non-exposed group. So if it's higher than 1, then we could roughly make the preliminary conclusion that the exposure might put people at a high risk of the disease of interest in our research. But if it's lower than 1, or very low, like 0.001, then we know that all the exposure might prevent people from getting the disease, right? In the scenario of the vaccination, there could be less than 1, right? Or physical activity, if you do more physical activity and less likely to get obesity or heart attack or diabetes, right? So it could be something higher or lower than 1. But in case control study, the relative risk is defined as odds ratio. Okay, the key point is that how we use the idea about odds to do the estimation of the relative risk in case control study. Characteristic of RR. First of all, I have to tell you that in some literature, they call it the risk ratio. But the relative risk is a more formal way to describe it. Okay? It's RR. The abbreviation is RR. It's exactly the same as the abbreviation of rate ratio, right? Another RR. But if you see something like risk ratio, it's just simply substitution of the relative risk. If something comes up without the unit, because of the ratio, so the numerator and denominator has to be the same in terms of unit. So if the denominator is incidence density, then the numerator has to be incidence density, right? If it's prevalence, then it has to be prevalence for both sides. Okay, so there's no unit. The unit has been eliminated. So all the ratio got no unit. Okay, but nowadays it's pretty easy to use a computer. It's very available and affordable. So if you report anything about relative risk, I would suggest you to show the uncertainty of the point estimation, or so-called 95% confidence interval. Okay, always come up with they're like twins. If you're reporting the estimation of relative risk, please remember to put the 95% confidence interval with it. It's kind of modern requirement. Because p-value does not satisfy science. It's just a probability. No matter how small the p-value is, there's still a possible that it's wrong, right? But 95% confidence interval will be able to give us have the more objective idea about the uncertainty. The narrower, the better, which means that we have a bigger sample size, or it's the nature of the estimation. It's more stable. So if the 95% interval is narrow, we have the better feeling about the certainty about the point estimation. Okay, so if possible, please do it. So odds, what is so-called odds? The odds is simply defined as the probability of something succeeds, or P, divided by the probability of something false, like 1 minus P. It's kind of ratio, but it's a specific kind of ratio. We call it odds. But why? Why do we need to create another term to describe such kind of ratio? Because we are going to do the calculation of the ratio by odds. If we don't give it another name, it will be the ratio of the ratio. That's very difficult to understand, right? So that's how Mr. Cornfield create such a term. The odds is defined as P divided by 1 minus P. They don't belong to each other, right? So no unit, but it's a special case of ratio. And in all the textbook, no one mentioned about that. This is something created by a person called Jeremy Cornfield. It's something published in a symposium back to 1956, just right after World War II. But people ignore his contribution until in 1980s, someone called the Greenhouse. It's interesting that both of them were about agriculture, right? Cornfield and greenhouse. What a coincidence. Very interesting coincidence, right? But anyway, Greenhouse was the one who highlighted the contribution of the Jeremy Cornfield's contribution to epidemiology, because he was the one who created a bridge to link the estimation of relative risk from different sides, from the prospective side and retrospective side. Okay, so the role of the odds ratio is like similar to the E equal to mc squared in physics. That's why it's so important in classic epidemiology. Okay, so like what I said, how we can judge or how we can define the study design in epidemiology. Timing is the key issue, right? So this is a simple 2x2 table. Exposure, yes, no. Outcome, yes, no. So people could be grouped in 4 different kind of situations. For A is yes, yes, right? For exposure and also outcome. And D means no, no, right? And B and C, yes, no, no, yes. Okay, so it's very simple. But if we consider the whole thing from the perspective of the status of exposure, and we follow up this group of people for a while, then it's cohort study. Right? I've mentioned it for many, many times. The estimation of relative risk for cohort study is straightforward again. It's rate ratio, which is defined as the A divided by A plus B, which is the total number of people exposed to something, right? And A is the number of people who got the disease. So this is the case of cumulative incidence. Divided by C divided by C plus D. So C plus D. Now here comes the key point. If the disease is rare in the study population, rare means that A and C are relatively smaller to B and D, or of course smaller than A plus B or C plus D. Okay, now we can ignore the A here or C there and make it like A divided by D and then divided by C divided by D. Okay, and rearrange the whole thing is AD over BC under the assumption of a rare disease. Okay, so this is acceptable, right? Not too difficult. And what if the study scenario is that we try to perform a study based on the status of disease in the very beginning, or so-called case control study. And we call it a retrospective view of the whole thing. Okay, in other words, we try to identify a group of people with specific disease comparing to the other group of people without the disease, and then ask them or check something in their blood or questionnaire or records about their exposure status before the onset of the disease or the time point of the interview for those without the disease. We could use something called odds ratio to do the estimation on their relative risk. Okay, because too crowded, so I skip one step here, but I'm showing here. Okay, so first of all, Mr. Cornfield, he was not a biostatistician and not an epidemiologist either. Yeah, he was a historian. Anyway, so now if we want to calculate the odds for cases, this odds of the exposure for cases, A divided by A plus C, right? Here. And to the C divided by A plus C. So it's exactly the same here. So it's A divided by C, right? So it's the same here. So it becomes B divided by D. Oops. Okay, so it's the A divided by C here for the cases, and the D divided by D for the controls. Okay, and I rearrange it, then AD over BC, right? So with the idea of odds ratio, he was the one who unified the bridge, and not he create or build up the bridge to make them the same, AD over BC, AD over BC. Yeah, very straightforward. In a single indicator, very straightforward for people to understand what's going on here, no matter what kind of study design. Because in case control study, we cannot do the calculation for rates or prevalence, right? Because we don't have the information about the denominator. So that's why he create or adopt the idea about odds and make it, see, exactly the same, AD over BC, under the assumption of rare disease. Okay, this is extremely important. Okay, so here's an example for exercise. Okay, it's a real story. I mean, it's a real data from the news. Try to translate it and describe it here. According to the data from official records of traffic accidents, which means the police records in Taiwan from 2011 to 2016, in total, there were 14,382 pedestrians involved in uncomplicated vehicle accidents, which means that it's not the accidents happening in the highway, it's not the serial car accidents, it's simply one vehicle, motorcycle or car, and people walking aside of those roads. When it happened, 10,749 pedestrians, or 74.7%, were walking along with the traffic direction. So in Taiwan, it's the right-hand side. Is there anyone came from the other country walking on the left side? No? Okay. Yeah, it's weird. It's difficult for me to walk or ride a bike in UK because people are walking or driving the wrong side for me. But if it's a one way, then either side is fine. And along with the traffic direction. Okay, thus 3,663 pedestrians, or 25.3, were walking in the opposite direction against the direction of traffic. Okay, but what's the point to pay attention to this kind of thing? Because if you are walking against or up in the opposite direction, you can try to escape at the last moment when the car or motorcycle is coming to you, right? But if you walk along with the direction, you have no idea about what's happening behind you, right? So it's pretty understandable hypothesis, right? Okay, so in these accidents, 199 people were killed, and consisting of 164 in the traffic direction and 35 against it. Okay, so with such complicated description about what's happening, is it possible for you to generate a 2x2 table to calculate the odds ratio for the death of walking in the traffic direction versus walking in the opposite direction? Okay, the key point is that the A, B, C, D in the previous slides is not randomly allocated. Okay, each of the letter means something specific. Okay, A means the number of people who had the disease and also have the exposure, right? And D means that neither for disease or exposure. So you need to rearrange the information given in the description to create a correct 2x2 table before you can do the correct calculation of odds ratio. Yeah, I've made it down, halfway down here, 2x2 table, A, B, C, D. Okay, translate the description here into such a simple thing for 2x2 table. Then I could create or could perform the calculation of odds ratio, which is a single indicator about what's going on for such a complicated thing. You might have noticed that there's no information about study design here, right? So how do we know that we have to calculate odds ratio rather than rate ratio? Because we don't have the information about all the people or a group of people working along with the direction or in the opposite direction at all, right? So it's not possible to do the calculation of rate ratio. So we have no choice to use odds ratio. That's the rationale behind it. So it's a great idea that even if we don't have denominator, we could still do a pretty precise estimation of the relative risk in a retrospective way, okay, for the comparison scenario. The first step is to rearrange the number in the 2x2 table in the right position for A, B, C, and D, right? And then you could do the AD over BC. So the answer is about 1.5 something, right? Okay, so how are we going to explain it? So the people walking along the traffic direction, they got a higher risk, and which is about 50% higher because it's a ratio, right, if they walk in the direction. If they walk against it, that's 1 because this is in the denominator for the odds ratio. Okay. And you might ask, what about the 95% confidence interval? If you use a computer, any kind of statistical software to do this calculation, it will give it to you automatically. Okay, so you don't need to worry too much. Okay, but roughly, you can do the estimation by yourself to see if the computer gives you the correct calculation outcome for it. About the assumption of the RR equal to OR, the RR here is the rate ratio equal to odds ratio. So the core study, the estimation of relative risk for core study is actually the same for the relative estimation for OR. The first one is that the cases are representative for the ones with the disease in the study population because we are supposed to get a random sample. That's the way, so-called random process, to help us to get representative cases. And also, with a random process, we could get a sample with representative control from the study population. So that's why we need to perform a random selection with a different kind of sampling methods, remember? And the disease is rare. Some people might ask, how rare is rare? 1 in 1,000 or 1 in 100? Actually, nowadays, a lot of biostatisticians has been trying hard to do the unbiased estimation and try to find out a better cutoff point about how rare is so-called rare here. And they found out that it has not need to be very rare. So even 20% is fine too, okay? And so there's no a definite or absolute number about the cutoff point about how rare is so rare. And so you don't need to worry too much about it. It has been proved fair or not so important in biostatistics. Personal insight, association is not equal to causal relationship. I'm going to highlight the idea about it in a lecture next Monday. Relative risk or odds ratio or rate ratio is the tool we use to assess the association for exposure and the outcome, or disease status to exposure. But it's not equal to causal relationship in science, so you have to keep it in mind. But it's a very important evidence about it, especially at the population level. Okay. If you are a molecular biologist, the story might be different. So it's very important to have a biological sense when we are trying to perform a study. So that's why I emphasize the idea about disease entity in the very beginning. Do you know how to play chess? Queen is superior than king, okay? So biological sense is the most important part of it. But data quality is also important, but it's the second one. And relative risk is not only powerful in studies for unknown disease, like what we do in the very beginning about the story for AIDS, or the story about traffic accidents for the pedestrian in Taiwan. Generally, that's the first step to do it's a simple estimation to give us some idea. If we find that it's particularly higher and particularly lower, then we might be able to generate and create another study, or perform another study to prove it with a more sophisticated measurement or statistical method, like confounding control. Here we did not consider anything about age and gender or anything else, right, for the calculation of the odds ratio for walking direction. But it's also useful for categorizing the existing disease at each stage. So in other words, it's also useful to compare the people who are alive or dead from a disease at the end of their life to the treatment, which is so-called clinical epidemiology. That's how we build up the chain of a causal relationship step by step. Okay, but for every stage, we could do something like that. We calculate the odds ratio as a preliminary evidence about it. So this is kind of summary for the lecture for this week. Risk is a fundamental concept about measurement in epidemiology, prevalence, incidence, and then we use the calculation or estimation of relative risk to assess the effect strength in etiology. So if it's much higher than 1 or much lower than 1, then we have the sense about it. But it's not the only evidence for causal inferences. I'll go into the detail next Monday. Read my lips. So it's very important to keep in mind that rate ratio, RR here is for core study, is an estimation of relative risk, which could be defined as odds ratio in case control study, or survey or cross-sectional studies. So the idea of odds is kind of a bridge to link the information or the numbers from different kind of study design. So the concept of odds ratio links the estimation of relative risk for core study and case control study. Only single number to give us some idea about what happened, okay, behind the complicated numbers. Okay? Thank you. So that's it.